Hey, good morning, folks. Happy Monday. Can you hear me?
Yes, ma'am.
You? Okay, fine. We'll start with today's class. Hope you can see the PPT. We are going to see some numericals today. Not exactly for mathematics, but let me just mute everyone. It's causing disturbance here. Fine. Um, I would suggest you to take down this question, everyone, because we are going to arrive on certain declarations on this question with respect to circuit switch networks and also packet switch networks. So I would suggest you to copy this in your note. Suppose a link transmits data at 1 Mbps rate. Consider a scenario where every user remains active for 10% of the time and transmits data at 100 kbps, and the rest 90% time the users remain inactive. If I say active, it means that they are transmitting data, or they are using the link. All right. When I say inactive, they do not transmit data. They remain idle. Okay. So with respect to this scenario, we are going to see what happens with the circuit switch network and what happens with the packet switch network. Fine. Okay, I hope everyone, I'll just wait for everyone to copy this down. And whatever declarations that I'm going to make, I want everyone to copy it down as well. Just give me a moment. So I repeat, suppose a link transmits data at 1 Mbps rate. Consider a scenario where every user remains active for 10% of the time and transmits data at 100 kbps, and the rest 90% time the users remain inactive. So what is going to happen in case of circuit switch networks and also in case of packet switch networks? So we have seen in the past two classes, we have seen what is the circuit switch network and what is a packet switch network. So we are going to arrive on certain declarations with respect to this scenario in circuit and packet switch networks. Okay, so I'm moving on. Hope everyone copied this. So I'm moving on to Microsoft Whiteboard. Suppose, assume that, not assume, just we'll just see a quick recap about one. Assume that there is a link with transmission rate of 1 Mbps. Okay, in case of circuit switched networks, all right, if it is 1 Mbps, all the systems connected to that network will share this 1 Mbps. Okay, assuming that there are systems 1, 2, 3, 4. Okay, in a circuit switched network, there are systems 1, 2, 3, and 4. All right. So what happens is, just give me a moment. Okay, what happens is, for example, there's system 1, system 2, system 3, and system 4. So all these connected networks to a circuit switch will be sharing a link of, I don't know what's happening here. There's some 250 kbps, and this will have 250 kbps. This system will have 250 kbps, because it's a circuit switch networks, each will have the whole 1 Mbps will be divided across these 4 systems, assuming that these are the only 4 systems connected to this particular network on a circuit switch. All right. So system 1 will have 250 kbps, system 2 will have 250 kbps, system 4 and 5, sorry, 3 and 4 will have 250 kbps respectively. All right. In case of circuit switch networks, the transmission rate is going to be very constant. Because look at the scenario, like if this one system needs to connect, talk to the fourth system, all right, this has a constant transmission rate of 250 kbps, and this will have remaining 250 and 250 that is occupied by 2 and 3 will just go unused. All right. So if these two wants to talk on a particular network 1 and 4, only whatever it holds, 1 will have a constant rate of 250, 4 will have a constant rate of 250. 2 and 3 are not doing anything, so they remain idle. So those 250 kbps will go waste. That's what happens in a circuit switch networks. What happens with respect to a packet switch network is the same scenario. Assume that there's a packet switch networks and there are systems 1, 2, 3, and 4. All right. So now these systems are interconnected. All right. So just give me a moment. This is so bad. What's happening with this pen? Okay, so assuming the transmission rate for this link is 1 Mbps, in a packet switched networks, the allocation is based on the demands. All right, here suppose 1 and 4 wants to communicate. All right, 500 kbps will be allocated here and 500 kbps will be allocated here. The remaining 2 doesn't want to talk. The remaining 2 doesn't get anything, wherein that is not in the case of circuit switch networks. Everyone connected to the network will have their share equally. All right, if they use it, they don't use it, that doesn't matter. That is not in the case of packet switched networks. Okay, having this short set this short note, we are moving on to the scenario we'll talk about. Okay, so we have considered a link at a rate 1 Mbps. Every user remains active for 10% of the time and transmits data at 100 kbps, and the rest 90% time all the users remain inactive. Okay, so we'll talk in terms of circuit switch networks now. Okay, please take down whatever I just you know, in case of circuit switched network, what happens in that scenario is, okay, the transmission rate the transmission rate the question says 100 kbps should be the transmission rate. So the transmission rate is 100 kbps. In case of a circuit switch network, this 100 kbps must be reserved for all the users. You got it right? Question says that the transmission data rate is at 100 kbps. So 100 kbps must be reserved for all the users. All right, because since all the connected devices gets a constant transfer rate in the case of circuit switch networks. So the total link transmission capacity is as per the question, it is 1 Mbps. All right, to find, therefore, if you want to find how many number of users can be there on this particular network, so the number of users on this particular circuit switch networks is 1 Mbps. 1 Mbps is in the sense into 10 to the power 6. kbps is into 10 to the power 3. Okay, so with that note, 1 Mbps is divided by 100, because the transmission rate is 100 kbps. So what you get, 10 to the power 6 into, here there's already 100 into 10 to the power 3, which gives you 10 as the answer. So the number of users who could use 1 Mbps link, each with a constant rate of 100 kbps, are only 10 users. All right, there can never be a 11th user in case of circuit switch networks in this scenario. Hope you understand, because everybody gets equal amount of transmission rate. So there can never be a 11th user here in the case of circuit switch network. So therefore no 11th, what's this, no 11th user in case of circuit switched networks. Right? So we have given a scenario in case of circuit switch networks, only 10 users can avail that. All right, we are moving on to packet switch networks now. Here we are going to see it in a different way, because we are not here, since it's a constant data transmission rate reserved for all the users. We can arrive on a conclusion that okay, these many users will be there. More than that many users not even one single person can add into it. All right, but that's not the scenario of packet switch networks. So in a packet switch network, please copy down. In a packet switched network, so as I said when I taught you packet switched network, right, the allocation will be based on the demand. How many our systems are there on a particular network, the allocation is only based on a demand. Okay, so here we, in the question, we have a rate of 1 Mbps. All right, so in case of circuit switch networks, we saw how this 1 Mbps is going to divide it, and how many users can be there. All right, but we can't arrive at a quick conclusion with respect to packet switch networks. So we have to find the probability. So the probability of one active user, as per the question, there can be 10 active users, right? User is active for 10% of the time. So the probability of one user active, I will call it as P. Okay, one user active is 0.1. That's because each user is active for 10% of the time. Assuming, suppose there are 35 users. I'm just taking it, 35 users. So the probability of having 10 users active users. Please mute yourselves. The probability of having 10 active users can be found, we will be using a binomial theorem here, can be found using a binomial theorem. Okay, summation of NCX into P to the power X into 1 minus P n minus X. Here X falls between the limits 0 and 10 because we are finding the probability of 10 users, 10 active users using a binomial theorem. So X falls in the limits of 0 to 10. All right, we are using a binomial theorem to arrive on a result for packet switch networks where P is nothing but 0.1 and N is nothing but, we are assuming it to be 35 users. All right, if you do a math on it, you will get a result which comes to an approximate number of this. Okay, 0.9996. So this is for 10 users being active. For the 11th user, having 11 or more simultaneous active users, you have to do, if you have copied this down, then I will just go to the next line. Okay. So therefore, having 11 or more active users, simultaneous active users, how do you find 1 minus 0.9996, which comes to 0.0004. All right, we cannot arrive on a exact number, how many number of users would be there for a particular scenario in case of a packet switched network. We have to just use a binomial theorem for that to have an approximate count. All right, so we use the binomial theorem to find the find the math which the total probability of 10 users being active. All right, so if you want 11 or more users to be active, 1 minus that. All right, so we are going to arrive on two certain things here. So hence, if the number of users transmitting data, or I would say I would call them as active users, is less than equal to 10, and if total arrival data rate is less than 1 Mbps, which is the link's capacity, there will be no delay. Can you just read this once again? The number of users transmitting data or active users who are less than 10, and if total arrival data rate is less than equal to 1 Mbps, there would be no delay in case of packet switch networks, because everything goes fine. 10 and 1 Mbps, even if it is based on the demand, no. If there are more number of users, consider the next scenario. I'm going to the next scenario. If you have copied this down, I'm going to the next scenario. Okay, the next scenario is if the active users are greater than 10 and arrival rate is also greater than 1 Mbps. Imagine what will happen on a packet switch network. I told you, if the arrival rate is going to be more than the link's capacity, all right, in this case, an output queue or a buffer comes into picture. Okay, that begins to grow. This output buffer will begin to grow until the incoming data date decreases. So there are two scenarios wherein you can look at this. If the arrival rate is greater, then output queue comes into picture, or the buffer comes into picture in a packet switch network. Or if it's less than 10 users, or if the arrival rate is less than 1 Mbps, which is the link's capacity, then nothing, there's no delay at all. It's just going to transmit the data. All right. So so we have taken 35 users, all right, and did this probability in case of a packet switch networks. Did you right? So when given a data transmission rate of a particular link at 1 Mbps, Okay, so there can be only 10 in case of a circuit switch networks. There can be approximately 35 users in case of a packet switched network. Okay, now you can see 10 here, 10 users here, 35 users in packet switch networks, almost 3 times the higher number of users than the circuit switch network. All right, hence packet switching networks is always highly efficient than the circuit switch network. So we can't exactly arrive on a count on a packet switch network. We have to only go with the binomial theorem. All right, and also there's one more point other than efficiency. There is better sharing capacity in packet switch networks rather than a circuit switch network. I will take a scenario and explain that as well. So what I would say is a packet switched network is highly efficient compared to a circuit switch network, and also a better sharing capacity. This sharing capacity is also good compared to a circuit switch networks. So we saw how it's highly efficient. In case of circuit switch networks, there were only 10 users and no 11th user at all. In case of packet switch networks, there could be approximately 35 users if you all right connected to a packet switch networks. Approximate count only I'm telling, right? That's why we say that it's highly efficient. Now we'll see how it is good in terms of sharing capacity. All right, I'll take one scenario and explain you this as well, how it's good in sharing capacity. So yeah,
Ma'am, I had a doubt.
I'll finish off this.
Okay, ma'am.
Yeah. So this next thing that I was saying is better sharing capacity. All right, how to justify this in a sense. Consider a scenario where there are 10 systems. And among this 10 system, one system wants to send 1 into 10 to the power 6. 10 lakh bits of data. Okay, and assume the link capacity is 1 Mbps. So we'll take this scenario to calculate which is better in terms of sharing capacity, whether it's CSN or PSN. All right, there are 10 systems. Among that, one wants to send 10 lakh bits of data with the total link capacity of 1 Mbps. All right, hope you have taken this. Okay, with respect to a circuit switched network, we will see the scenario. All right, assuming that it uses TDM, because circuit switch networks can be implemented either by TDM or FDM, right? We saw that. So since here every user has a dedicated capacity of 100 kbps. Why 100 kbps? Because 10 users, 10 systems, 1 Mbps, so divided by 10 you will get 100 kbps. So I will write here, in case of TDM, every user has a dedicated capacity of 100 kbps. How did I arrive on this 100 kbps? Because the link is 1 mbps. All right, the total number of systems are 10 here, so each will have equal sharing here, so that's why I said 100 kbps. All right, so since if you want to calculate the time taken to transmit 10 lakh bits of data, that's what was given in the scenario, 1 2 3 4 5 6 is equal to 10 to the power of 6 divided by 100 kbps. 100 kbps will become, kbps is 10 to the power 5, it's already 100, so it is 10 to the power, sorry, kbps is 10 to the power 3, already there's 100, so to calculate this it will be 10 to the power 5, so it is 10 seconds. All right, to transmit this many data in this link, you will have 10 seconds in a CSN which uses TDM technology. All right, the same in case of a packet switch network. In a packet switch network, the same scenario, it's very easy because it's based on the demand. The allocation is based on the demand. All right, it's a 1 mbps link, and there's only one system who's going to transmit that data. So time taken to transmit data will be only 1 second because it's only one active user. So all the whole complete transmission links capacity will be given to that particular user alone. All right. So in this case, the time taken to transmit these many number of bits in a packet switch network will be only 1 second because the total capacity is 1 mbps. 1 mbps is 10 to the power of 6. All right, so it's just one second because it's only one active user as per the scenario, so it's only 1 second. So in the case of circuit switch network it was 10 seconds, and in case of packet switch networks it was just 1 second. Here it's all of them are reserving this 1 mbps link. All right, where here it is just based on the demand. So definitely the sharing capacity is good in PSN with respect to than the CSN. All right, so we are just arriving on conclusions here. I just wanted to know how you have to arrive on conclusions here. That's it. So just a quick gist of what all we saw now. Okay, so we have considered a scenario where every user remains active for 10% of the time and transmits data at 100 kbps. The total link capacity is 1 mbps. All right. With respect to a circuit switch network, the transmission rate 100 kbps must be reserved for all the users since all the connected devices get a constant transfer rate. So the number of users in a circuit switch network will be 10 because it's 1 mbps divided by 100 kbps, so it would be 10. So with respect to packet switch networks, that we can't just find out in a very straightforward way. We have to go with a binomial theorem, as the experts say. So we have to see the probability of one active user and take some number of users. Here we assume that there were 35 users, and the probability of having 10 active users simultaneously can be found using the binomial theorem. And this was what I said. So, right. N minus x, where n is 35 and x falls in the range of 0 to 10, and p is 0.1, the probability of one active user. So that comes roughly to 0.9996, wherein this is only for 10 users. If you want to find it for the remaining users, 1 minus 0.9996, which becomes 0.0004. All right. So since we have assumed 35, so this falls good for 35 users. So for on a PSN, we can have 35 users on the same scenario, wherein on a CSN, we can only have 10, not even the 11th one. All right. So there is 3 times higher, 3 times, higher efficiency or higher number of users. So obviously the efficiency is good in a PSN. So when you think of an internet, it is all about PSN. All right. CSN is only about the old traditional telephone systems and the radio systems. All right. So when you think of PSN, it's your current internet today. All right. So in case of so we saw two conditions where if the number of users transmitting data or active users is less than equal to 10 and the arrival rate is less than 1 Mbps, less than equal to 1 Mbps. So there's going to be no delay with respect to packet switch networks. But if the arrival rate increases and also the active users increases, there could be a possibility of this buffer coming into picture, wherein you have to find the queuing delay also there. All right. So we saw in terms of better sharing capacity, CSN is good. All right. So having said this, I just finish off this also and come back to the question. Hope you can see this. Packet switching versus circuit switching, numerical example. How long does it take to send a file of? Just take some 2-3 minutes to figure out this. If you don't get the answer, don't worry. I will anyhow tell you. How long does it take to send a file of 6,40,000 bits from a host A to host B over a CSN? Here there are 3 points given. All links are 1.536 Mbps. So they have talked about CSN. So all links will only have 1.536. Each link uses TDM with 24 slots per second. And there's extra 500 milliseconds to establish a end-to-end circuit. Just think of the total time taken to send a file of this many bits, 6,40,000 bits, with all these given conditions. Just think of how to arrive on this. Just take 2 minutes time to arrive on this. We will work out on this as well. So Mbps is 10 to the power 6, kbps is 10 to the power 3. Gigabytes per second is 10 to the power 9. This is just a note. So the question is how long it does to take the end-to-end time. That's it. Hope you're figuring it out. Okay, we'll figure it out. So the first one is each circuit has a transmission rate of 1.536 Mbps. That's what is given there in the question. Since it uses TDM, there are 24 slots per second. So we have to figure out one circuit transmission rate in a circuit switched network. All right, because a circuit should be established. The whole link capacity is this. Out of that, each link uses 24 slots per second. So you have to find each circuit's transmission rate. So I simply divide 1.536 Mbps divided by 24. I'll just take a calculator. Okay, 1.536 into 10 to the power 6. So I will just simply put it as 1536 into 10 to the power 6 becomes this. Hope you can see the calculator, right? Divided by, since it's 24 slots per second, which becomes 64,000. So this 64,000, when you want to have it as kbps, kbps is always 10 to the power 3, so it's 64 kbps. So 10 to the power 3, so I divide by 1000, so it's 64 kbps. All right, so each circuit has the transmission rate of 64 kbps. So now you have a file of 6,40,000 bits and you have a circuit of 64 kbps. It's easy to find how much of time it needs to transmit that particular file. So by answer we can say 6,40,000 bits divided by L by R. Rate is 64 into 10 to the power 3. So the answer is, we need not do a math on this, it's just 10. So 10 seconds to transmit the file. Fine. But there's one more given in the question. So it takes 500 milliseconds to establish an end-to-end circuit. So end-to-end is a circuit link, transmission rate is this much and all. The end-to-end means from the host system to the first circuit, to the circuit. How long, what time it takes to establish a connection is, they have given in the question, it's 500 milliseconds. So the total 10 plus adding the circuit's establishment time. So it is taking 10.5 seconds to send the file. right? Okay, fine. All right, we'll stop the class right now. Somebody had some doubt. Can you post this to my mail ID? Deepa Shri, right?
Yes, ma'am.
Can you post this to my mail ID?
Yes, ma'am.
All right, thank you. So I want you to just go through whatever is taught today. Then we will see the next topics tomorrow. Right? Thank you.